Today we're diving into the fascinating world of multiplexers, commonly known as MUX and demultiplexers or DEMUX. These components are essential in digital electronics, especially when it comes to managing and routing data efficiently. Whether you're a student, an engineer, or just curious about how information travels inside devices, understanding MUX and DEMUX is a great starting point. In this video, we'll break down what these devices are, how they work, and why they're so important in modern technology. Let's get started by exploring the basic concepts behind multiplexing and demultiplexing. Multiplexer, or MUX, is a digital switch that selects one input from several and forwards it to a single output line. Imagine you have multiple data sources but only one communication channel. The MUX helps you choose which data source gets to use the channel at any given time. This selection is controlled by special input signals called select lines. Multiplexers are widely used in communication systems, data routing, and even in everyday electronics like your smartphone. They help reduce the number of wires needed and make data transmission more efficient. The flip side, a demultiplexer or DMUX takes a single input and channels it to one of many outputs. Think of it as a traffic controller that directs a single stream of data to the right destination among several possible paths. DMUX devices are crucial when you need to distribute information from one source to multiple destinations, such as in digital TV broadcasting or data distribution networks. Like MUX, DMUX also uses select lines to determine which output path the input data should follow. Why do we need multiplexers and demultiplexers? In digital systems, resources like communication lines and data buses are limited. MUX and DMUX help optimize these resources by allowing multiple signals to share a single channel and then separating them at the destination. This not only saves hardware but also reduces costs and complexity. Without these devices, we'd need a dedicated line for every signal, which is impractical in large systems. Typical multiplexer consists of multiple data input lines, a single output line, and several select lines. The select lines determine which input is connected to the output at any moment. For example, a 4-to-1 multiplexer has 4 inputs, 2 select lines, and 1 output. The select lines act like a code, telling the MUX which input to pass through. This structure is the foundation for more complex data routing in digital circuits. Demultiplexer has a single data input, multiple output lines, and select lines. The select lines decide which output line the input data will be sent to. For instance, a 1-to-4 DMUX has 1 input, 2 select lines, and 4 outputs. This setup allows a single data stream to be distributed to different destinations as needed, making it ideal for applications like data distribution and signal routing. Let's look at a simple example. Suppose you have 4 sensors collecting data, but only one data line to send information to a processor. A 4-to-1 multiplexer can connect each sensor to the processor one at a time, based on the select lines. This way, all sensors share the same data line efficiently, and the processor can read data from each sensor in turn without extra wiring. Now imagine you have a single data source like a computer that needs to send information to 4 different devices. A 1-to-4 demultiplexer can direct the data to the correct device based on the select lines. This ensures that each device receives the right information at the right time, all while using just one data input line. Select lines are the control signals that tell the MUX or DEMUX which input or output to use. The number of select lines depends on the number of inputs or outputs. For example, 2 select lines can control 4 inputs or outputs, since 2 equals 4. This binary selection process is at the heart of how multiplexers and demultiplexers operate. The truth table is a handy way to show how a multiplexer works. It lists all possible combinations of select line values and shows which input is connected to the output for each combination. This helps designers and engineers understand and predict the behavior of the MUX in different scenarios. Similarly, a demultiplexer's truth table shows how the select lines determine which output receives the input data. Each combination of select line values corresponds to a different output being activated. This table is essential for designing circuits that use DEMUX devices, ensuring that data is routed correctly. Multiplexers come in various sizes, such as 2-to-1, 4-to-1, 8-to-1, and even 16-to-1. The first number indicates the number of inputs, while the second is always one output. The choice of size depends on the application and how many data sources need to be managed. Larger MUX devices can handle more inputs but require more select lines. Multiplexers are also available in different sizes, like 1-to-2, 1-to-4, 1-to-8, and 1-to-16. Here, the first number is the single input, and the second is the number of outputs. The size you choose depends on how many destinations you need to send data to. Larger DEMUX devices can distribute data to more outputs, but again, they require more select lines. Multiplexers are widely used in communication systems to combine multiple signals into one for transmission over a single channel. This is especially useful in telephone networks, where many calls are sent over the same wire, and in digital TV, where multiple channels share the same frequency band. MUX devices make efficient use of available bandwidth and infrastructure. At the receiving end, demultiplexers separate the combined signals and send them to their respective destinations. This process is crucial in ensuring that each user or device receives the correct information. Without DEMUX, it would be impossible to efficiently distribute data from a shared channel to multiple endpoints. In computer systems, multiplexers are used to route data between different parts of the system. For example, a processor might use a MUX to select which memory location to read from or write to. This flexibility allows for more efficient use of hardware and faster data processing. Demultiplexers are equally important in data distribution. When a single data source needs to send information to multiple destinations, a DEMUX ensures that each destination receives the correct data. This is common in memory addressing, where a single address line can select among many memory cells. You might be surprised to learn that multiplexers are found in many everyday devices. For instance, your smartphone uses MUX circuits to manage signals from different sensors, cameras, and communication modules. This allows the device to operate smoothly without needing separate wiring for each component. In digital TV broadcasting, demultiplexers play a key role in separating multiple channels sent over a single signal. When you change channels on your TV, a DEMUX inside the receiver directs the correct channel's data to your screen, ensuring you see the program you selected. In computer networks, MUX and DEMUX devices are used to manage data traffic. Multiplexers combine data streams from different users for transmission, while demultiplexers separate them at the receiving end. This process is essential for efficient use of network bandwidth and infrastructure. Storage devices like hard drives and SSDs use multiplexers and demultiplexers to manage data flow between the storage medium and the computer. This allows for faster data access and more efficient use of storage resources, contributing to the high performance of modern computers. Embedded systems like those in cars or appliances often use MUX and DEMUX to control various sensors and actuators. By sharing data lines, these systems can be made smaller, cheaper, and more reliable, which is crucial in cost-sensitive and space-constrained applications. Multiplexers offer several advantages. They reduce the number of wires needed, save space, and lower costs. They also make it easier to expand systems, since adding more inputs only requires more select lines, not more physical connections. This scalability is a big reason why MUX devices are so popular. Demultiplexers also bring important benefits. They allow a single data source to serve multiple destinations, making systems more flexible and efficient. DEMUX devices simplify circuit design and make it easier to manage complex data distribution tasks, especially in large-scale digital systems. Despite their advantages, multiplexers have some limitations. As the number of inputs increases, so does the complexity of the select logic. There's also a limit to how fast a MUX can switch between inputs, which can affect performance in high-speed systems. Designers must balance these factors when choosing a MUX. Demultiplexers also face challenges. As the number of outputs increases, the select logic becomes more complicated. There's also the risk of signal loss or interference if the circuit isn't designed properly. These factors must be considered to ensure reliable data distribution. To handle more inputs than a single MUX can manage, designers often cascade multiple multiplexers together. This means connecting the outputs of several smaller MUX devices to create a larger, more capable system. Cascading is a common technique in complex digital circuits. Similarly, demultiplexers can be cascaded to increase the number of outputs. By connecting multiple DEMUX devices, you can distribute data to a larger number of destinations. This approach is useful in large-scale systems where many outputs are required. Time division multiplexing (TDM) is a technique where multiple signals share the same channel by taking turns. Multiplexers and demultiplexers are key components in TDM systems, ensuring that each signal is sent and received at the right time. This method is widely used in telecommunications and data networks. Frequency division multiplexing (FDM) is another technique where multiple signals are sent over the same channel, but each uses a different frequency. MUX and DEMUX devices help combine and separate these signals, making FDM possible in radio, TV, and broadband communication systems. In digital circuits, MUX and DEMUX are often implemented using logic gates. These gates control the flow of data based on the select lines, ensuring that information travels to the right place at the right time. Understanding how these circuits work is key to designing efficient digital systems. Microprocessors use multiplexers and demultiplexers to manage data flow between the CPU, memory, and peripherals. This allows the processor to communicate with multiple devices using a limited number of data lines, improving efficiency and reducing hardware requirements. Control systems, such as those in industrial automation, use MUX and DEMUX to manage signals from sensors and to control actuators. By efficiently routing data, these devices help ensure that the system operates smoothly and responds quickly to changing conditions. Audio and video systems often use multiplexers and demultiplexers to manage multiple input and output channels. For example, a home theater receiver might use a MUX to select between different audio sources and a DEMUX to send sound to various speakers. In robotics, multiplexers and demultiplexers help manage signals from multiple sensors and control various motors or actuators. This allows robots to perform complex tasks with fewer wires and simpler control circuits, making them more efficient and reliable. Modern cars use MUX and DEMUX devices to manage communication between different electronic modules, such as the engine control unit, infotainment system, and safety sensors. This reduces wiring complexity and improves reliability, which is critical in automotive design. Industrial automation systems rely on multiplexers and demultiplexers to control machinery, monitor sensors, and manage data flow. These devices help factories operate more efficiently by streamlining communication and reducing the need for extensive wiring. When designing digital systems, engineers must carefully choose the right type and size of multiplexer or demultiplexer. Factors like the number of inputs or outputs, speed requirements, and available space all play a role. Simulation tools can help test designs before building physical circuits. Testing is a crucial step in ensuring that MUX and DEMUX circuits work as intended. Engineers use test benches and simulation software to check for errors, verify timing, and ensure reliable operation. Proper testing helps prevent costly mistakes in the final product. If a MUX or DEMUX circuit isn't working correctly, engineers troubleshoot by checking connections, verifying select line logic, and testing each input and output. Common issues include wiring mistakes, faulty components, or incorrect select line signals. Systematic troubleshooting helps quickly identify and fix problems. As technology advances, multiplexers and demultiplexers are becoming faster, smaller, and more efficient. Innovations in materials and design are pushing the limits of what these devices can do, enabling new applications in fields like quantum computing and advanced communications. In quantum computing, researchers are exploring new types of multiplexers and demultiplexers to manage quantum bits or qubits. These devices must operate at extremely high speeds and with incredible precision, presenting unique challenges and opportunities for innovation. The Internet of Things, IoT, relies heavily on multiplexers and demultiplexers to connect countless sensors and devices. By efficiently managing data flow, these components help make smart homes, cities, and industries possible, paving the way for a more connected world. To sum up, multiplexers and demultiplexers are vital components in digital electronics, enabling efficient data routing and distribution. They help reduce wiring, save costs, and make complex systems possible. From communication networks to everyday devices, MUX and DEMUX play a crucial role in modern technology. Thank you for joining us on this journey through multiplexers and demultiplexers. We've explored their structures, uses, advantages, and limitations. As you continue learning about digital electronics, keep in mind how MUX and DEMUX simplify and empower modern technology. Stay curious and keep exploring the world of electronics.